So we get broadening of the emission line, kind of like thermal broadening. It's basically due to a distribution of velocities of the emitting atoms, but it's a different underlying physical effect because, of course, it's rotation, not a thermal effect. So let's just look at what's going on in this figure. We have the star rotating. Now this is what you see due to this point on the star. Here, what they've done is they haven't made this a perfectly narrow line. Even at this point on the star, that's not perfectly narrow. It's got a little bit of width to it. That's because they're taking into account the fact that the star itself is going to be hot. So we're kind of mixing together rotational and thermal broadening here. So if you could just look at this side of the star, if we had a telescope that allowed you to look at just the side of the star that was rotating toward you, you actually would still see a little bit of broadening because of the temperature of the star there. And over here, if we could look at the receiving side of the star, you'd also see a little bell-shaped curve with a little bit of width due to the temperature. But as I said a moment ago, we can't actually observe individual parts. It all gets mixed together. So this is what's actually seen, this outer curve here. So that outer curve, if you think about it, is actually a combination of rotational and thermal broadening. They're both contributing to that wide curve that we see over there. And actually, it's a little bit difficult to tease apart how much of each of these two effects are involved. You really can't do it merely by looking at one profile like that. You don't know. I mean, it could be a really hot star that's not rotating, or it could be a really cold star that's rotating really fast, because both of those would lead to broadening. So as a matter of fact, we actually have to use additional information, which usually comes down to observations of the specific line profiles, the specific line distributions that we see. Because the line distributions, the actual lines in the spectrum, tell us about the composition, right? But it turns out that the line patterns we see also tell us about the temperature, because as we crank up the temperature, we get more ionization. And when you ionize, you rip atoms apart, and that changes the line pattern too. So the bottom line is that we can independently estimate the temperature, and then that allows us to tease apart the two effects of rotational and thermal broadening. So, what we've just seen in the last chapter is a variety of different ways that we can extract information from light. That's really the bottom line. We can't reach out and touch any star, not even the sun. It's all done remotely, so that one of the biggest games in astronomy is just figuring out how can you extract information from this light, which is being provided by free. It's coming into a stream from the cosmos, and if we can decode that, we can learn about the composition and physical properties of the source. All right, so that's kind of the theory end of things. Now, when we start talking about actually collecting light, we're talking about telescopes. So that's why we move on to chapter 5 here. We have the good old Hubble, which is still up for another couple of years, I think, doing its thing, and has really revolutionized astronomy in many ways, many of the observations that it's done with Hubble. Okay, so we're just going to start off with some of the basic concepts here. Astronomers sometimes call telescopes light buckets, because telescopes always have a certain diameter, which is sometimes called an aperture, but it's just a diameter. And just like a bucket will collect rain, obviously you put a larger diameter bucket, you're going to collect more rain per hour. That's pretty much a no-brainer. Well, telescopes work exactly the same way, because the light is just like rain coming down. The larger we make the telescope, the more light we're going to collect. So larger telescopes are going to collect more light. And that's the essential reason that larger telescopes are better and more useful, simply because they actually absorb more light from a given source. What we're going to talk about first are optical telescopes. When we say optical telescopes, they utilize visible light. So we can put an eyepiece in an optical telescope and actually just observe directly with our eye without taking photographs if we don't want to do that. And just to, again, go back to this idea of larger telescopes. So, of course, if we collect more light, we can obviously look at fainter objects, collecting more light. Fainter objects usually mean more distant objects, so we can look at more distant galaxies. And we can also, as it turns out, magnify more and obtain more fine little details. So that's another thing that we get from larger telescopes. You see brighter images and more detailed images. So the two major categories of telescopes are reflectors and refractors. Telescopes have to focus the light to an eyepiece or some kind of recording device. But they have to focus the light. If they don't focus the light, they're no better than just a cardboard tube or something like that. They have to focus the light to concentrate it and be able to use it. There's two ways that we can concentrate the light and focus it, and that gives rise to the two basic types of telescopes that we have here. We have reflecting telescopes and refracting telescopes. Reflecting telescopes have a mirror, we'll see down at the bottom, and the light comes in, they open into the tube up here and gets reflected off the mirror, which is a curved mirror. So the light comes together and then passes through another secondary mirror, an eyepiece. We can accomplish the same thing using refractors, which are sort of the telescopes we think of when we think of Galileo or Pyrex or something like that, eyeglasses. They use lenses to focus light that's incident on the lens to pass through an eyepiece down at the other end. Now there's a little short YouTube video. It's not really worth too much, but at least it's something different to look at. I think it's only about a minute long, so I just got to show you that.
There's two sides of Washington, D.C. There's the side that tourists see.
Okay. There's the side that tourists see.
So you have a telescope. I don't know whether you have a refractor or a reflecting telescope, and there's a wide variety of telescopes. The basic telescopes, though, are either a refractor or reflector. Now, we think of a refractor as the old type that pirates used. This is off of a fairly cheap telescope that we've had around the observatory for about 20 years. And it has a lens in the front and a lens in the back. The light comes through the front and it focuses it out the eyepiece. In a reflecting telescope, it uses a mirror instead of a piece of glass. They both do the same thing. They both form a light cone. Light hits the mirror, bounces off, and comes to a point, and you intercept that point with an eyepiece. They both are light buckets. They gather as much light as they possibly can based on the diameter of the mirror of the lens. So think of a telescope as a light bucket.
Okay, good. So we can see here that good. So, yeah, the bigger bucket, actually there's more rain here, same depth, but because it's got a larger area, there's more volume, so that's just like the analogy of the telescope collecting more light. All right, so let's go through this a little more detail. Focusing on reflector and focusing on reflector. But anyway, let's talk about reflector telescopes first. So we have to cause the light to focus to something we call focal point. And that's accomplished in a reflecting telescope using a parabolically curved mirror. So this curvature here actually is a parabolic shape if you want to slide it. There's a mathematical reason why that particular shape actually will cause light incident on any part of the surface to focus to the same focal point. And of course that's critical because it won't form an image if we don't focus the light at the same focal point. In a typical reflecting telescope, this is what we call a Newtonian telescope, there's actually a secondary mirror that reflects the light out of the eyepiece. You actually could view it directly at what we call the prime focus if we don't have a secondary mirror. But the catch is that the prime focus is inside the telescope, so you either have to cram your head in the telescope, which is kind of a fool's errand, because if you cram your head in there, you're not going to see anything because you're going to be blocking the light. So early telescope designs were a disaster because they didn't work because everybody said, this is going to work, and then you put your head there and you're like, it's all dark, what's going on? But then they got around it because they realized that their head was simply, blocking the flow of photons. So we have invention by Isaac Newton of a secondary mirror, which then sends the light out the side when your head's on the leg. Now, having said that, if you have a large enough telescope, a giant telescope, you could actually be at the prime focus. Your whole body could be at the prime focus. If the mirror is so large that you're not really blocking very much of the light by hanging out at the prime focus. So that's kind of like nirvana for astronomers, to be at the prime focus with the light actually comes in off of a huge telescope. And I'll show you some photos of really large telescopes, like, for example, the Palomar telescope in California, which is a huge telescope. All right, so I mentioned that there's all the light incident on the mirror focuses at the same point, and you notice that the shape has to be a certain shape, because when we have rays coming in on the edge of the mirror, they have to reflect by a larger angle in order to reach the focus right there. Now, rays coming in closer to the axis of the mirror would actually reflect through a smaller angle. So, you have to the shape of the mirror comes from the fact that you've got to make sure that deflection angle is exactly right at every point along the mirror so that you're focused at the same focal point. And that turns out to be a parabolically shaped mirror. And the focal length is the difference between the mirror and the focal point, or focus right there. So this is a mirror. This is a reflecting telescope. Now, if we look at the formation of an image, this is kind of cool because occasionally there have been problems with astronomical reflecting telescopes where there's damage to part of the mirror. And then you might think, well, if there's damage to some part of the mirror, you're going to have like a hole in your image or something like that. You're going to have a blind spot in your image maybe because part of the mirror got damaged. Actually, it doesn't work that way because the way it actually works is every single point on the mirror makes its own contribution to the complete image. So the more of the mirror that gets, messed up, well, if it's really messed up, you might have to like spray paint it black or something like that so it doesn't reflect anymore. But whatever's left is still going to contribute to the same actual image. And so if you cover a mirror with cardboard or something like that, what actually happens is you still see the image, but it gets dimmer and dimmer because you're getting less contribution of radiation from those parts that aren't working anymore. And then, of course, you cover it completely, obviously, it just goes out. So if we look at what's going on here, we look at light from a comet here, light from the top of the source is the yellow part, light from the bottom of the source is the purple part. And what we find when we form the image is that it just is turned upside down. No big surprise there because we're dealing with a mirror after all. So we see that typical inversion. But again, every point on the mirror actually contributes to the formation of the image. So moving on to talk about refracting telescopes, we call them refracting telescopes because they have a lens at the upper end of the telescope, and the focusing occurs by refraction through the lens. Now remember, when we looked at prisms, you can create a spectrum using a prism. The reason that works is because the prism refracts light of different wavelengths, different angular amounts. That actually could be a problem, primary lens or reflecting telescopes. Because if you think about it, there's a potential there to screw up a colored image, because if the lens acts like a prism, you could end up with a screwed out image. So that's something we'll get to called chromatic aberration. All right, so we have light entering the telescope at one end, coming in parallel from a distant source, and we see focusing to a focal point. So again, we have the concept of the focal length, from the lens to the focal point, and then an eye. Okay, so we're doing this with the lens now. This is the same design used by Galileo. So it's pretty much the standard thing that we think about when we think about a telescope. So we're going to be talking about the drawbacks and advantages of both of these types of designs. All right, so if we look at the lens, we have incoming light rays that are all parallel. We get the focusing effect, and it's from the focal point, from the focal length. Okay, so this is just considering refractors and reflectors separately next to each other. And what we see is that we're forming an image two different ways. So we have here light coming in along the prime axis here, gets focused by the primary mirror, to the secondary mirror, out to the eyepiece. Same thing with the starlight coming in through the lens. Now, one thing that's assumed here is that all the light is coming in parallel to the axis of the telescope. If it comes in off axis, it actually doesn't get focused with the same focus length. So you might think this could be a problem, but the thing is, all the astronomical sources are so far away that the light reaching us really is parallel to that axis, very high accuracy, so we can focus to a single